All right. Good afternoon, everyone. And it is my pleasure to have Professor Yogender Kumar Mishra today, who is the professor and leader on the smart material at University of South Denmark. And it is indeed pleasure on behalf of IEEE Nanotechnology Council South Africa chapter, as well as Academy of Nanotechnology and Wastewater Innovations, South Africa, to have Professor Yogendra Kumar Mishra with us. He is going to talk about the tetrapod based 3D smart material for advanced technology. I want to give him a brief introduction about him, that he is a professor at MSO at Mats Clausen Institute, University of South Denmark. Prior joining to South Denmark University, he was leading a scientifically independent group at Functional Nanomaterial Chair Institute for Material Science, Kiel University, Germany. He did habilitation in material science from Kiel University in 2015 and PhD in physics in 2008 from Jawaharlal Nehru University, New Delhi, India. He introduced a new flame-based process for versatile nanostructuring of metal oxide and 3D interconnected network. This zinc oxide tetrapod found many application in engineering, in biomedical fields, and additionally, they can be used as sacrificial template to create hybrid new materials. So there is a lot, and he's a world renowned, scientist, and it is a pleasure to have him today with us. And again, I want to thank him to accept the invitation on behalf of IEEE Nanotechnology Council and Academy of Nanotechnology and Wastewater Innovation. So now over to you, Professor Mishra.
Yeah, good afternoon, everyone, and thank you very much, Professor Mishra, for inviting me to talk about our research in the IEEE chapter from South Africa about nanotechnology. I'm very much pleased to talk about it. And today I'm going to introduce our research activities based on tetrapods, and three-dimensional smart materials. Yeah, so before I switch to the real topic, I would like to give a brief introduction about the university. It's called the University of Southern Denmark. This is more or less covering the entire southern Denmark region from Copenhagen to nearly, this is the Germany border, more or less. And there are different campuses located in many cities. Odense is the main center where the main university is there, and we are located here in Sonderborg. So you can see all around water everywhere, and that's what also motivates us to work with water as well. These are some facts and figures from the universities, although they have been improved. They are the numbers from the last year. So there are a large number of programs which are offered from our university in terms of international masters and also bachelor's PhD. So please feel free to browse through, and if you are interested, you are most welcome. We are located in SDU Sonderborg. It's a kind of a small institute, a small part of Faculty of Engineering called Mats Clausen Institute and Nanosud. This is how the building looks like. We are just on the bank of the water, which is a very beautiful campus with kind of lot of equipments, including clean room characterization techniques, fabrication, roll-to-roll, and kind of advanced. So we have three campuses here. One is working in the direction of nanos with the smart materials, and the other is focusing on the energy center for industrial electronics, and we have center for industrial mechatronics. So there are a lot of young students who are working in a very nice environment here. We represent more than 91 nationalities here with a good clean room and equipment. We are very well equipped for advanced state-of research. So we are very much open for welcoming new students, and also we are very much open for new collaborations, whatever is possible. So it's most welcome. If you find something interesting, please feel free to contact me or to colleagues on the website. Yeah, so with this, I would like to switch to the topic. Today's topic is nanotechnology 2.0 and why do we need three-dimensional nanomaterials. I mean, we are talking about nanomaterials since nearly 3 to 4 decades after the lecture from the Feynman, this famous lecture, and more or less these nanoscale materials, they are very small in size. When we make the nanomaterials in a kind of a smaller in size, what happens that the surface contribution goes higher and higher. Basically, you all have probably studied in your defect lectures or in solid state physics lecture, the surface of any material itself is a defect because the periodicity is broken, the continuity is broken, and we have the dangling bond. So if we are reducing the number, the size of the material, going down to the nanoscale, it's much more surface. So the surface becomes very, very energetically active. And that's why we have these nanoscale material, these nanoscopic materials with many new extraordinary properties. In last 2-3 decades, we have really understood, we have developed many class of nanomaterials, whether they are spherical particles, nanowires, nanotubes, nanowells, whatever it is. They have been developed by many methods, physical methods, chemical methods, biological methods, and there are probably a large number of methods which have been used to develop, synthesize different kinds of nanomaterials. They have been synthesized, they have been investigated with respect to their structure property relationship. They are and more or less they are very well understood in terms of their properties, and indeed they exhibit very nice properties. However, despite of these 4-5 decades of nanotechnology, we are having very advanced equipments to really understand their property. But if we ask around, is there any product which is based on nanomaterials and we are using in our daily life? There are not many answers available. And we are now, since last decade from 2010 and currently in 2021, we are undergoing a great transformation in nanotechnology. That's why we coined the term nanotechnology 2.0. That means that now we are going to address the most important question: how we bring these nanoscale materials into the real applications. Into the applications in our daily life technologies. But there, what are the challenges? Suppose we want to make a sensor out of a nanowire, what do we need? We need to make a nanowire first, which is a very small size, probably the diameter of 100 nanometer. But then we need to connect this nanowire with the external circuit. That is very very difficult task because you need nanoscale interconnections, and we are going to the clean room often to make these nanoscale sensing devices. Very fine, they work very fantastically. Their performance is also quite good. But if we think about upscaling, then the problem is they are too much expensive. They are very, very expensive. So we have the problem of upscaling. We cannot make many more. So there is a challenge. That's a great challenge in terms of having the nanomaterial and integrating it into a proper kind of device form, or integrating it into a kind of composite form, or making or using. So basically, challenge is how to efficiently use those nanoscale properties in a larger system is the most important and open challenge. And we got motivated with this challenge. Okay, let's work on this aspect. That was our key motivation previously before. What we learned something from the glass rod and the glass fiber. You all know very well, if you try to bend a glass rod, it is going to break down. It's brittle in nature, conventional ceramic. But same glass, if the same glass is used to build the fiber, these are very thin fibers. You have the possibility to fold and put into the pocket. So you get the flexibility aspect. So if the aspect ratio is large, curvature is higher, they can be bent to larger curvatures. Imagine if our hair is 1 centimeter thick, it is not going to bend. But if it is a few micron, we are able easily, we are able to easily fold them like we want. So from this aspect, we got motivated. Okay, we need to develop a certain form of material where we have accessibility to nanoscale features still, but at the same time it is large enough so that we are able to connect to the external kind of devices. For example, if we want to make a sensor, or we want to integrate into kind of cloth, or if we want to integrate in any form of composite or mount somewhere, this should be. And the answer comes from your kitchen very nicely. If you see the kitchen sponge, this is made out of certain kind of polymer material. Imagine if this was a solid block of polymer, it was of no use. You cannot bend it, you cannot use it. But probably it is 1/100th of the same block which has been used to construct this sponge out of that material. Now it has opened multiple use. And these are some kind of one-dimensional structures interconnected together in form of a three-dimensional sponge. Here we have the possibility of accessing the nice polymeric properties, for example. At the same time, this is the best example how architecture can introduce new properties into the material system.